We're given a cantilever beam with span L that is loaded with a uniformly distributed load W applied in the entire span. An upward force P is loaded at the midspan of the beam, with value equivalent to WL. If W equals 20 kilonewtons per meter and the length is equals 5 meters and EI, or deflectional rigidity, is constant, we are tasked to compute the value for the slope at the point where P is applied and the value of deflection at the point where P is applied. And to solve this problem a lot easier, we'll be using the area moment method to solve for the value of the slope and deflection of this cantilever beam where P is applied. So P here has a value equal to W times L, where W equals 20 kilonewtons per meter and the value for the length is 5 meters, giving us the value for P that is equals 20 times 5, that is equals 100 kilonewtons. Now to solve this problem, let's solve for the reaction at the support that has a moment induced and a vertical and horizontal force at the fixed end. Let's call this Rx and Ry. So taking summation force vertical equal to 0, we have Ry plus the 100 kilonewton force going upwards minus the uniform distributed load of 20 kilonewton per meters times an overall length of 5 meters, all equal to 0. Now solving for Ry, we have 20 times 5, that's 100 kilonewtons, all equal to 0, and 100 minus 100, that's equal to 0. So the reaction at Ry is just equal to 0. So there is no vertical force exerted by the fixed support. And by taking summation force horizontal, by inspection Rx is just equal to 0. And for the moment at the fixed support, we take summation moment at this point here. Let's call this point A, all equal to 0, considering counterclockwise to be positive. We have the uniform load of 20 kilonewtons per meter times the length of 5 meters multiplied by moment arm distance of 2.5 meters. And the sign here is negative because this will induce a clockwise moment. And then for the concentrated load of 100 kilonewton, that would induce a counterclockwise moment, so it's positive. We multiply this by the moment arm distance of 2.5 meters. We also have this moment induced by the fixed support that is going counterclockwise, so we add this up by m and equating the entire equation by 0. We can solve for m. That is a value equal to 0. So there is no moment induced at the fixed support, which means that the fixed support does not induce any reaction at all for this beam. Now to solve this problem using area moment method, first we will establish a reference line where we will draw our moment diagram by parts. So let's say it's right at the center of this cantilever beam, and then we take the moment induced by all reactions and forces found in this beam. So we have the uniform distributed load on the left side that would induce a moment about this reference line here, that is a value equal to 20 kilonewton per meter times this length of 2.5 meters multiplied by moment arm distance of 2.5 over 2. So we have 20 times a length of 2.5 times the moment arm distance of 2.5 over 2. This will create a moment induced by this uniform load on the left about this reference line that has a value equal to 62.5. And for this uniform load here on the right, this will induce a moment about this reference line that has a value equal to 20 times the length of 2.5 to get the resultant times a moment arm distance of 2.5 over 2. That has an exact value that is also equal to 62.5, which will create another second degree curve. on the right. To solve for the slope using area moment method, the change of the slope between two tangent lines at points A and B is just equal to the area of the moment diagram by parts between A and B. So to solve for the slope at this point here, at the center where B is applied, in reference to the tangent drawn at A, so since this is a fixed support, therefore the tangent line at the fixed support is just a horizontal line, and assuming our elastic curve somehow looks like this, the slope at the point where B is applied is just the change in slope in reference to the tangent drawn at A and to the tangent drawn at the midspan, which is at point B. Let's call this here point B. This is the slope, and that's just equal to the area of the moment diagram by parts between A and B, which is this area right here. And that area of this second degree curve, which is a parabolic curve, is just equal to 1/3 times the base of 2.5 times the height of 62.5. This is just equal to 52.083 over EI, which is letter B. Now to compute the deflection at the point where B is applied, using the same concept of the area moment method, the tangential deviation at point B relative to the tangent drawn at point A, which is this one. So the tangent deviation at point B, which is at this point here on the elastic curve, in reference to this tangent drawn here at A, is just the deflection at B in reference to the tangent line drawn at A. That is equal to the area of the moment diagram by parts multiplied by the centroid of point B in reference to the vertical line we drawn. So the area of the moment diagram between A and B is equal to 1/3 times the base of 2.5 times the height of 62.5. Multiply this by the distance going from the center of this curve here to the reference line. That is a value equal to 1/4 of the length of the parabolic curve, which is 2.5 meters. And this is a value equal to 32.55. And we divide this by the flexural rigidity. And these are our final answers.